Hello and welcome to our online VPIphotonics users group meeting. In the next 60 minutes, we would be honored to show our most recent developments, which we included in VPI Design Suite 11.4 version. So this includes our generic capabilities of the Photonic Design Environment and VPIphotonics Analyzer, so the tools we are using for the analysis of the signals, as well as improvements in our application-specific solutions, so optical transmission systems, free space optical links, integrated photonics, and laser design. And just a reminder, we also have all the features described in the release notes document, so you can access it here, as well as on our website. So if you couldn't attend the Q&A session, or if you are watching the recording of this webinar, please do not hesitate to email us at support@vpiphotonics.com. We are always happy to help and empower you to define the cutting edge. So before we dive into the details, let me please introduce myself. I'm Eugene Sokolov. I will be moderating the webinar today, and my colleagues Nebras Depp and Shuli also joining me today, and we'll be sharing some of the features on different topics. And with that, I give the floor to Nebras Depp. Nebras, please, the floor is yours.
Good. So yeah, I'm excited to show you the new features in the new release 11.4, as Eugene mentioned. And let's start with the first feature about which focuses on ways to work with our schematics and specifically about stripping a module instant from a link. So just a reminder about previous capabilities that we had. So here we have a simple schematic. We have a laser source. We are filtering this laser source. We have an attenuator here which applies a sweep, and just looking at the power at the output. So you know, from previous releases, we can right click on a module and deactivate it. And so this is very helpful, which means that the signal can then, in this case, will pass through the optical filter without being processed. So that's with a click of a button, which is very convenient. Also, we had this capability to exclude a module, but it should be usually in the end. So excluding the module means it's not in the calculation of it's not in the simulation anymore. So it's just excluded from the simulation setup. But for some modules, actually, like this module here, if you right click on it, you see that you cannot deactivate it. So you find this with some modules, and you may decide if you want to remove it from the schematic to delete it. And that's another option, right? So you can simply delete it. But if you delete it, you will lose all the connections here and you will need to rewire. So I'll just undo this change and it's back. So now there's a new capability that you can right click on it and strip it. And this means it will be removed and the wiring will be done automatically. So I find this very convenient. Now we have removed it. So another capability that's also a reminder is that you can say we have an attenuator that you would like to insert into a link. So you can now, and this is from the previous release as well, just put it on the link like this and hold it for some time, just for a second, and you will find that it's added automatically here. Okay, so we can now, if we run it, you see here, you can look at the spectrum and the power at the output. Okay, so strip, and there is a shortcut for this. So if you, for any module, if you press on your keyboard, Shift and Delete, that will strip the module from the link and rewire automatically. Okay, so that's the first feature. Now let's move to the second feature about duplicating schematic parameters. So this is now possible. A similar setup that we see here. We have a single laser source. Now if we see here, the emission frequency for this laser source is assigned from a global parameter, emission frequency 1. So if we look here, double click, show the parameter editor. So that's a global parameter, emission frequency 1, that's assigned to this laser source. Okay, so let me fit all and say I want to add another laser source here. So I have a multiplexer here, as you see. So I can, you know, that I can do Control-C, Control-V, or copy and paste a module, and then link it here to this, to the input of the multiplexer. And now, because I have two inputs, I want to modify the channel number for the multiplexer to be 2. Okay, but now I want to actually, you know, copy the parameter, the global parameter here, and assign it to this new other module. So how do I do this? Previously, it was a little bit, it would take time to do this. So it was not possible to duplicate a schematic parameter. Now it's simply you can right click on a parameter and choose duplicate parameter. And this will create a copy of this parameter. And most importantly, it's not only the value that we have here and the name of the parameter. So let me change the value to 193.2. So it's 100 gigahertz apart from the other one. But also, if you notice here, so you know that we have this button here, which shows the parameter properties for this newly created parameter. So it copied all the attributes from the previous parameter. So you don't have to specify them again. The unit, the type of the parameter, the minimum maximum value, default value, etc. So this is also very convenient. And you know, now the next step would be just to assign this new name to the second laser source. And if we run it, we save and run. Or probably first I want to deactivate this filter so it would be more clear to see. And you have now the two laser sources here directly. Okay, so this is I find it very convenient that now you can duplicate schematic parameters. Another feature is about inserting images. So say we have this schematic where we are designing a multi-section tunable laser diode, and it's based on our Photonics TLM module that's available in our VPI photonic circuit maker. And so now say I would like to add an image to an illustration for this device. And previously, it was a little bit not straightforward. We used to have to go to graphics, insert images. So we had this capability of inserting images, but it was a little bit hard to add a. So we need to do several steps and do the keep original size, for example, or sorry. So resize, and then you need to do like this, and then you can point to the image which you would like to insert. Now it's much more easier. You can simply, if you have an image in your, say you have a PDF file, that's where your image is, this image, I can use the snipping tool, for example, and directly have the image here. And you know, here in the snipping tool, I can copy it, and now I can paste directly into the schematic. So you see this here, so it's added, and I can mirror it if needed for the X or Y axis, rotate it like this, or I can resize it. And if you press Shift, by the way, on the keyboard, then you would be preserving the ratios for the height and width for this image. Okay, so you can start thinking about the schematic or the universe here being more like a container where you can put your, you can put your descriptions, you can put your files, right, PDFs or images, and you can insert images here, illustration images. So it's very flexible and very convenient for using. So it can contain all your related papers, for example, and resources. Okay, so this is also very convenient. Now another new feature is labeled links. So what is this about? So you know that we have these links between modules, right? And in previous releases, a link can be like this. It can be a wire or a bus, and a bus means multiple wires, right, or multiple connections between two modules. Now we have added a new type of the link, and it's called labeled. And this was basically a demand actually by some users of the software, especially people working on switching or ROADMs and this kind of applications. So the thing is that we want to add not only descriptions to the links, but also to manage these links in a better way. So here you see that I'll zoom in. So we have this source, the transmitter pulse array, which produces a group of channels at the output. And here, using the just the labels, I'm specifying how many channels I'm producing at the output in this case. So this is not only a text, but it's also you manage the link with it, and you manage the schematic with it. Several things can be done with this technique using the labels of the links. For example, we can merge odd and even channels, like in this case. So here you see I specified the channel indexes and a step of 2 from 21 to 42, while here is from 22 to 42. So odd and even channels. I can also, so you see I have here a multiplexer and a demultiplexer. I can add and drop channels, like here I'm taking 5 channels to view on this analyzer. I'm also adding 5 channels using this source. So using this this command add 28. So using this formula, and yeah, and then I will be showing on this spectrum analyzer. I can show both, actually, all the channels and the 5 added channels. So if we run this, I can show you here in the analyzer. So you see here we have the added channels directly here, and I have multiple inputs. So these are, because that's after the demultiplexer. So I can control which channels I'm showing, right, using the input selector. By the way, these here are very attenuated channels. So these are not real channels, but very attenuated channels. And if you remove, you are left with nothing in the end. Okay. So let's go back, and just if you'd like, if you are interested more in this concept, this is based on this demo. There is also probing capability with this technique, so you can refer to this demo here. You will have the recording file. You find it on this path, and you will find more details about this concept. Also, more details about how the formatting and the syntax for that we use for labeling links. It's all mentioned here in chapter 3 of the simulation guide. You can also refer to this. Now, another nice feature is, when you run a schematic, we have the message log, right? So whenever every schematic you run, you will find messages about when it started, when it finished. There might be warnings. There might be also, you may have in your scripts, you produce some results here. So previously, everything is mixed together. But now, with the new release, you can now choose which messages, or just choose the messages, or filter them based on the schematic. So I can show the messages which relate to this run of this schematic, okay, or to the last run, or to all. All right. So you have this also new capability. So all these features, very nice for the GUI. And let's now talk about the new features for the VPIphotonics analyzer. I'll just focus on these features. And again, as Eugene mentioned, in the release notes, you will find a list and explanation of all the features for both GUI and the VPIphotonics analyzer. So in this feature, in this schematic, you will see here I have simply a transmitter based on an electro-absorption modulator, and I have a PAM source here. This is electrical here at this point. The signal is electrical. I will be viewing it. I have a filter that mimics the bandwidth limitation of the EAM. This will produce delay, but I also have more delay, let's say a representation of the electronics there. And will be comparing the signal from before and after filtering and delay. Okay, so for an electrical signal. So let's run this and look at the analyzer. So these are the signals before filtering. Okay, this is before the filter and this is after the filter. And if I want to compare these two traces together, I can right-click on this trace and copy it and simply paste it here. So I can look at both. But because there is delay, it's hard to really understand how these two compare together. I can rename this trace and call it after filter. Okay, and I'll copy it. So, all right, but now a new capability is that if you go to the control panel, you can add a trace and a trace or a new trace that is a shifted version of this blue line here, all right, or this trace. So we go here, we go to math in the control panel, and at the very bottom here, add edit trace. So we need to use a specific formula for this. So say I want to do the shift on the x-axis, right? Because we want to do a shift in the time. So here between the brackets, we're going to type the name of the new trace. So that's after filter, let's say shifted. So this can be arbitrary name, and this equals the same thing. Let's say, but without the word shifted, right? So here. Okay, and this is coming from this blue trace, and in the end, I'm going to subtract 0.25, and that's in nanosecond in the end because it uses the unit that is used here on the axis. We have added a new trace and it applied the name for it. All right, so now it's much easier to compare the new trace with the original trace. You know, also we can delete this added trace before shifting, and we just keep the original trace before filter and after filter, but shifted. So it's much easier to compare. Now you can write many types of expressions, many operations. So we shifted on the x-axis. You can shift on the y-axis instead. And more details about this, let me go back to the schematic, are found in here. Also in the simulation guide, you will find there what operations are allowed, what you can do, how to change from like to do the shift or the operation for the y-axis or for the x-axis or other. All right. Now let me go back there and show you another very nice capability about zooming in. So previously to zoom into traces, you needed to click and drag like this. Now you can simply use the scroll. So control and scroll of the mouse button, and you do like this. You're zooming in and out. And also you can zoom in and out for the axis like this. So if you bring the mouse closer to the axis like this, see? And then you can zoom in and out for an axis, keeping the y-axis unchanged or the opposite here. Okay, so these are the features for the which I wanted to show for the GUI and the VPIphotonics analyzer. And let's now proceed with the yeah, I'm happy to hear your questions in the Q&A sessions, by the way, or in the chat. And let's now proceed with the next set of features which focus on the optical systems. So also there are several improvements in the optical systems, and let's start with the first one, focusing on equalizers. So there are several improvements now with the equalization, and you know, equalizers. There's a continuous interest in this, especially in short-reach systems, about using the feed-forward equalization and decision feedback equalization, especially these two equalization algorithms. So now this demo here, this schematic, it may look big. It's based on one of our demos. You can find it in this location in the short-reach folder, PAM-4 400G Ethernet over single-mode fiber. But you can look at the boxes, which simplifies it. Now you will find that if you look at previous releases, we used to have a DFE here, a decision feedback equalizer module here. So now a new feature is that the DFE and the FFE have been added as new algorithms in our DSP library module. You may be familiar with this module. This is used mostly in our coherent systems, and it provides access to our library of algorithms. So you find the different algorithms for timing and sampling, equalization, all the algorithms for coherent detection you can find them here. And now if you look at the equalization and POL-D-MUX, you find that in addition to what we had before, we have now the DFE and FFE. So previously we had these modules. We had the FE and the FFE implemented only in electrical domain, not with the DSP. So now it is available here, and if you look at the help here for this module for the DSP, you can, you know, that there is a table here If you go down the module reference, there's a table that with links to all the algorithms supported with this library, and you find here about the DFE and FFE. So these are new. You can look at more details about this, and of course, in the end of this module reference, you find references for all these algorithms. Okay, so this brings an advantage. One advantage is about the sampling rate. So previously you used to have for DFE and FFE, they used to work only with one sample per symbol, while now you can use it with at any sampling per symbol, basically. For example, 2 samples per symbol or other. Another new feature here for this, a new capability for DFE and FFE, that now they both support, you can operate them with data aided or decision directed. So with data aided, of course, you want to add the reference. So here by default, we have it we have it for decision directed, all right, and it's for DFE. You see the feedback coefficients, but now you also can switch to data aided, and this is especially nice for FFE because we did not have this capability before to use it with data aided, and you can then provide the name of the file for which provides the data. In this case, it's coming from this module. So here at this point, you see there, I'll just zoom in. So we are taking at this point at the transmitter side, we are saving the data to use it as a reference here at the receiver side with this algorithm. Okay, with the DFE. So this is another nice advantage for it. You see that, yeah, if we just want to compare with what we had before with the previous DFE, FFE, we used to have them in electrical, so you can recognize this from the color of the port. All right, so here we had it now, it can operate with like with the DSP library here, with the DSP module, with a matrix float or float matrix. And you know that if you point to any, if you look at this area here down, if you point to any port, it will tell you the data type, right? So it's float matrix for this port, while for this lower port, it's float, because it's only passes the sampling rate from one DSP module to another. So this opens the door to new possibilities for you for when working with using the DSP modules, especially in short reach systems. Okay, so it's very, very flexible, very nice. Now also, if we now again, if you know that the exclude, I can include all here. So previously we excluded this. Actually, I want to run this quickly to show you the results for this. It just takes a few seconds to finish, and you start to see the results here. This is before DSP, and this is after DSP, right? And in this case, we are using DFE, and again, you see a great improvement in the SER, or the simple error ratio, right? From 1e to the -3 to 6 to e to the -5. Here you have also the PDFs before and after DSP. Let's go back, and here, if I include all, I just want to show you also what we have here, the new, for the electrical DFE and FFE modules, they have changed, so they are more convenient now. So this is based on one of our demos, the PAM-4 optical interconnect, also this setup, and you will see that this demo is updated now in 11.4. You will see that this module now, we have the FFE and DFE, and the Volterra equalizer now is moved to a different, a separate module. Okay. Also now the DFE and FFE are optimized for PAM-4, and previously DFE was optimal for NRZ only. All right, and this is about the equalizers. I hope you will enjoy this feature. And let's move on to the next application example. And this is a new application example focusing on optical frequency comp. You know, there is always there is interest in optical frequency comps for WDM systems. They provide several advantages compared to multiple laser sources. They give you stability of the spacing between channels. In this example, we have 50 gigahertz spacing. So you have one, you know, you are starting with one laser source instead of multiple laser sources. So spacing, easy to adjust, and also it enables spectral efficiency for transmission systems, as you know, and energy saving in WDM systems. So now it's in this application example, you see that it's you can easily adjust the frequency comps. Here we are producing 9 tones, all right, at the transmitter side using this MZM based optical frequency comp. And then we are applying modulation to all these 9 channels. And then this is a single polarization and 16 QAM as a modulation format. We're doing transmission over multiple loops of the fiber. I think this is 400 kilometers. Sorry, it's 200 kilometers. And then we are doing coherent detection here at the receiver side. And after the ADC, we are doing the standard DSP stages to retrieve the signal. And you can also look at the new demo. You will find it also in the software in 11.4 that relates to this. And one very nice thing about this is that you will see you have this filter here. We are filtering in before the receiver. We are using optical filtering to select one channel, okay, of these channels, and we specify that simply with a parameter, which is comb blind index. So that could be anything from 1 to 9. So if we go to the global parameters, so it's basically adjusted here. We specify the channel spacing here. We specify the comb blind index, as you see, and we can also sweep this. Okay, and that's used then by with the here to select which channels is being filtered using this optical filter. So we are in this case we are detecting channel 6, but we can also run a sweep as I implemented here, and you can sweep this. I just chose to do it between 2 and 8. You can do it from 1 to 9 for all the channels, and let's run it. And you will find also that here in this result here that we are showing, we show also the impact of the DC source over the biasing of the MZM and how it affects for number 5, for channel number 5, how it affects the SER. So we have SER versus DC voltage, so you can optimize the biasing of the Mach-Zehnder modulator for this channel. Okay, so let's look at the sweep now. And you see, we start to see the results, and this is the spectrum for all the channels, and this is before modulation, right? These are all the tones. We have 9 tones, and these are the modulated channels. And we look at the constellation here. Of course, one polarization, and also we look at the SER here for the different tones or the different comb lines. All right, for these 9 channels. And the channels here, because we are just controlling that index, it's just sweeping which channel is being detected. We can also do a nice thing here. We can, you know, that we here in mode, if we are choosing single, so we can navigate between the channels, right? But we can also instead use superimposed and show them all from 1 to 7. So in this case, 7 refers to the channel number 8, right? Because I chose 2 to 8. So you see all the channels here just shown together, right? You can also copy all traces and put them here and paste. So they all show, like you compare with the original channels, right? So in this case, we are not showing 1 and 9. Okay, so a very nice new capability as well. So, and let's go then to the next one, which is about Gardner clock recovery algorithm. So, what is this? This is basically a newly added algorithm to our DSP library, basically, but it's added using co-simulation. So, you know that here in the DSP library, we can add a user-defined algorithm. We can, and this is good to demonstrate how you can add a new algorithm to your library, user-defined using Python or MATLAB. So previously we had a clock recovery algorithm, and it was based, as you see here, if you look at the help of this module, the DSP algorithm, the DSP library, it was based on Euler-Meyer algorithm, and this is the reference for it. This is reference number 1. All right, but this algorithm, it has some limitations, and it helps to correct the clock frequency mismatch between the transmitter and the receiver. So here that's reflected in the sampling rate of the ADC, and you see here. So we have some relative clock frequency mismatch, and the clock recovery algorithm would correct for this. But this is the older one, which we had in previous releases, had its limitation, and that's reflected in this figure here, as you see. Okay, so the green line here is for the older algorithm, for the Euler-Meyer algorithm, and you see here SER versus clock frequency mismatch. So it shows that it doesn't perform well with larger values of clock frequency mismatch. Now the newly added algorithm, which is called the Gardner algorithm, and its modified version that's included here. This was updated recently. You can look at the references here, 2 and 3. Okay. The newly added algorithm performs much better with larger values of frequency mismatch, as you see here. Okay, that's with the blue line, as you see. And currently it works with at a fixed 2 samples per symbol. This is what it requires. Right, so let's run it quickly and we'll see. So again, here we have a loop, and we are doing dual polarization 16 QAM. We have 5 loops of 80 kilometer single mode fiber, and yeah, and a nice thing about this algorithm, it's also modulation agnostic to modulation format. So it works with QPSK, 16 QAM, or 64 QAM. So here we see that the constellation. And that this is actually using the older algorithm. And if we run this sweep, oops, I need to close the previous sweep here and come back and run this. Just to quickly compare between the Euler-Meyer algorithm and the Gardner algorithm. So I'm going to close the previous group of results, close active group. And here it shows the directly. See, this is the SER using the older algorithm that we had in previous releases, and this is the SER using the new algorithm. All right, and here you can navigate between the two, looking at the constellation as you see for Y polarization. Okay, so I also hope that this is useful to you or your applications, and I think now at this point I have finished this section for optical systems, and it's time to switch gears to free space optics, and that's presented by Shi.
Hi, my name is Shi. So I'm gonna show you our latest features for the free space optics part. So let me share my screen. So just a reminder, so we have here in the project folder, and for this today, everything that we show you is in this project folder. But maybe a little bit a step back. So we have now separated in this newest release free space optics and in terms of the modules. So previously it was hidden in the fiber folder section, but now we decided, because we want to avoid confusion, we decided to add another folder structure folder into the module library, which you can see here. So it's called now free space, and all the modules that is concerning the free space optical channel will be then placed in this part, as well as in the resource tree, our application examples. Previously, it was put into the sort reach folder channel folder structure, but now we have a dedicated folder that is also called free space, where you can then see all the available application examples, demos that uses the channel model for free space optics. Now, let's talk about the latest feature that we have for this release. So I have prepared 3 demos. The first is to showcase our enhancement that we have now for this atmospheric channel model. So it first of all has a new name. Now it's called FSO_channel Atmo. And we greatly enhanced then the scintillation calculations for uplink and downlink, which can now support quite a bit of the type of different link types. That means that you can now are able to also simulate airborne use cases for high altitude platforms, so hubs and airplanes, drones, and so on. So this is now available, and with that we can use with the Gaussian approximation, Gaussian beam approximation, we added additional new features and parameters to it. So for this, for example, we can now add a constant pointing error to the uplink and downlink use cases, and then also add this beam wander effect. And you can see on the right that the performance will greatly change if you consider pointing error. So the pointing error is not just for the physical pointing error, but it will also influence the calculation for the scintillation index as well. So that's why what you can see is that for a given zenith angle, given elevation angle, the BR performance with and without the pointing error and with and without the beam wander effect will then also change. For the downlink, which is more crucial and more apparent, is we have added then the aperture averaging effect. So here we use in downlink the plane wave approximation, what you can also see here in this figure here. So in this calculation, when we use the plane wave approximation, we can apply aperture averaging. This is automatically done in the parameter editor. And with that, you can see that also the aperture averaging will have an effect on the scintillation index itself, and therefore it will also have an impact on the system performance as well. We have also included additional turbulence profiles to it. So previously in the earlier versions, it was still very tedious to add or implement the turbulence profiles. So when you open the parameter editor from this channel, then what you previously could do is you could then set the CN² parameter either by adding the complex equation to it. But now for this release, we have now included several turbulence profiles directly into this channel model, so you can very conveniently and very easily then switch between the different models that are natively now implemented. However, you still can then use your user-defined approach to then select or to then add your own turbulence profile to the system or to the channel itself. The last important feature that I want to showcase here is importance sampling. So since scintillation is a random effect, it's statistically or it needs to be statistically run several times in order to have a very good approximation of the scintillation effect overall. It is very inefficient, or it is very hard to look at specific wear events or wear occasions. And with importance sampling, what it allows you to do is to set in the parameter to importance sampling and then to set the level of the scintillation directly. So this means you can directly choose a wear event where the scintillation occurs very rarely. And this way, it allows you to reduce the number of simulations that you have to do in order to account for those specific rare occasions and events, right? So this is something that will greatly reduce the simulation time. You do not need to run several hundred or thousand times in order to get a good statistics for that. You can directly then look at the rare worst case scenarios to simulate it in those events and those use cases. So this is all for the enhancement of this specific atmospheric channel model. The next model is the intersatellite channel. So we have implemented in this release now, or we have added in this release a new intersatellite channel module, which accounts for the power fluctuation of the pointing jitter using the Raytheon PDF, and also for the Doppler effect. So you can see that here, since we do not have scintillation effects, the power fluctuations comes from the mechanical jittering between them, or due to the movement of the satellite itself. And this can be approximated by the Raytheon PDF statistics. And since we have now the communication between satellites, in this particular example, we have a communication between LEO and a geosatellite. We need to consider the relative velocity between those 2 points, between the transmitter and the receiver, for example, and therefore we need to account for the Doppler effect. And this means that at the end of the day, that the frequency will be shifted during the transmission, and this has to be accounted for, which is now available in this intersatellite channel module. And depending on the phi angle that you can set, the relative velocity between those 2 satellites will change, and therefore also the Doppler shift. And for that, you can then use a conventional digital signal processing or the new Gardner signal process algorithm to then compensate for this Doppler shift, for this frequency shift. Another new added feature is a macro that allows you to quickly ascertain certain link budget properties of the FSO link itself. This link budget is, or this macro is usable for both our channel modules. In this particular instance, we have it as a resource in the intersatellite channel application example. So when you select this module and double click on this macro, then what will happen is it will create open up a GUI that that will showcase then all the link parameters of the channel, and then give you quickly an overview of the link budget itself. So here in this particular instance, the received power. So when you do this, and the only thing that you need then to add is the transmitted power. So if you then select then or type in the power, the launch power, so we have now 33, but since we have a coupling loss a little bit, we have 32 dBm. Then what will happen is you will then you can directly calculate the received power of this link, and therefore you can directly see the output or the outcome of the values that you have to set in order to have a certain received power value, right? And this is the same as if you would simulate the whole entire system. So let's do this. So let's run it once. And what you will see, if you run this simulation once, you will then see the result of the BR versus received optical power, and the value will be the same. So now it's run again. So here you can see the BR versus received optical power, and the power is the same as if you would use the link budget macro to quickly ascertain if the received power is enough or not. We have also here included several sweep mechanics here, so you can quickly sweep the pointing error for different bias settings here. So with that, if it will quickly run through, you can then evaluate the performance for a specific bias of a pointing error bias here. So you can see that it gets worse if the bias set is increasing. Now, this is all what we have for the new intersatellite channel module. And the last feature that we have is another approach. It's the phase screen approach. So it's a complete wave front analysis for turbulent free space channels. So this approach looks at the beam profile and uses several phase screens to then calculate and analyzes the output of the beam profile. So what it does is, so when we start with a, let's say, Gaussian beam profile, and we have several phase screens that are independent to each other, it will, using the Kolmogorov model and the Hufnager-Valley model, can emulate the turbulences for certain altitudes. So here we have in total 11 phase screens that are placed for at different altitudes. And if we set things in a certain way using enough phase screens, what the output would be is the distortion due to the turbulence effects in the atmosphere. And you can see that here you can then analyze the wavefront disturbances, not just for the amplitude, but then also for the phase. And this is another way how you can analyze the changes or distortions which comes then which also will impact the phase of the beam itself. In this particular instance, it is for a downlink from a satellite to the ground station with several phase screens layers to emulate then the distortions of the atmosphere. And as you can see, this demo is separated in two parts. So the first part is to generate the phase screen, the transfer function of the phase screen, and the second one is to then propagate the initial beam profile through those phase screens. So I've already generated the first step. So what you can see is the created transfer function for each of the phase screens. So if you double click on that, you can see it is really just a text file with given parameters of x and y plus the phase. And so you can also very easily implement your own transfer functions for those phase screens. So once you have done that, you can just run the second step, and you can see this is usually very quickly done. And this module or this step allows you then also to look at the beam profile for each of the phase screens, or after each of the phase screens, after each of the optical elements. And until then you see the last beam profile after all the phase screens. So here would be the last one after 11 optical elements. And then you can go through each of them and also save it for further processing the beam profile.
Yeah, thank you so much, Nebras. Thank you so much, Shiv, for your presentations and walking us through the improvements in VPI Transmission Maker Optical Systems tool. And now I completely switch the gears from satellites, long distances to really short one, because we're going to talk about the integrated photonics and the components which are modeled actually on a chip. And just to give you a brief reminder that we have this tool, VPI Component Maker Photonic Circuits, and I'm sure we have the users of this tool right now in this meeting. The purpose of this tool is actually provide the solutions for the design of integrated photonic circuits. And for that, we have the library. So we have peak elements, we have laser sections, which provide the models for specific components, and we constantly improve those components and extend the library. So for example, in this release, we improved stability of our SOA measured model. And also improved accuracy of modeling the group delay, because of the specifics, the group delays are really important in integrated photonics applications. But we also extended our library. So although in general our components are pretty much platform agnostic, so for example, one waveguide could be used both for simulating the silicon nitride or silicon or indium phosphide materials. We started adding some components more specific to the materials. So we added a silicon microring modulator model in some previous releases. And in this release, we added periodically poled lithium niobate waveguide. So why did we do that? So in the first place, because of the increased interest in the nonlinear optical effects, including second harmonic and some frequency generation. And among all other materials, the lithium niobate really performs good, pretty high second order nonlinear characteristics, so we account for those. But still, it is pretty small, and in order to improve the nonlinear response, some structural improvements are needed. So in this particular case, we account for periodically pole structure, which basically ensures that the phase mismatch and improves the nonlinear response. So one of the peculiarities about this model, so here this guy, so that because one of the main applications is actually generation second harmonic, which means that our frequency is like twice large as the original frequency. And this means that we need that large frequency bandwidth, which is for sure not applicable because it would be, the simulation would take forever. So because of that, we have not so common two outputs of one waveguide. So one is for original frequency and another for the second harmonic. So let me run the simulation. In this case, we just simply mix two signals, 500 gigahertz apart, right? And then here the result. So those are our original frequencies, and those are second harmonic generation, and also some generation. So we can switch also to the micrometers, and see that we moved from the traditional C-bands to pretty much optical visible wavelength. Okay, so that's a useful module. If you're working with these kind of applications, please go ahead, give us your feedback. We are still improving it. We are still working on it. So in addition to improving the models, we also extend the usability of working with our existing models. And one of the most advanced we have is Photonics TLM model. And in this release, we added a specific macro called Visualize Photonics TLM Structure. So this model in general is capable of simulating very wide range of the devices, including SOAs and the lasers and electron absorption modulators. And so this macro actually helps to understand for the users to understand the internal structure, and you can see it alongside with other macros we added previously, which also help the users to understand what's going on inside. So in this macro, let me run it for this guy, for example. For a simple single device section device, it's relatively easy. It just shows the type of the section, so it is color coded. So this 10 color denotes the active region. So we have here the denotation for the grading as well. But it's not that useful because the structure is pretty simple, right? However, we also support modeling the multi-sectional devices. So merely it means that in one component within one module, we can simulate multiple sections. So this could be electron absorption modulator, SOA, gain section, phase, some Breck reflectors. And the way we specify parameters in this case, we use arrays, right? So you see different length of different sections are just separated by space, and this becomes already pretty complicated to understand what's going on here. And in this case, this macro is really very useful since it gives us this insight of the internal structure of different relations between different length. If we assign the grading properly, as we can see here, right? So some of the passive sections, which are denoted with this blue color, have grading, some of them don't. It also shows how our contacts allocated, so where go the different electrical inputs. And in this case, we have this DBR-based laser integrated with SOA and with electron absorption modulator module. And another use case is that the number of sections could be even more, especially if we are talking about the repetitive structures, as for example, this sample grading. So in sample grading, we have interleaving parts with grading and without grading. and this gives some improved characteristics of those gratings. Yeah, we can specify the parameters in a more compact way. So in these square braces, just as a reminder, in these square braces, we specify the number of repetitions. But again, with increasing number of the sections, understanding what's going on inside could be a tedious task. And yeah, and having this macro we find very, very useful. So again, we are working on this macro, improving it. So please, yeah, give us your feedback, and it's very likely be included in the next release as well. And the very last thing, as you all know, that in addition to the components, we also have the whole library of application examples, and we are constantly working on extending those libraries and adding new applications for the cutting edge technologies. And for this release, we actually added a couple examples, which one could use as a template for your own designs, which target LiDAR applications, and more particularly frequency modulated continuous wave LiDAR systems. And you know, in general, those kind of applications are a bit out of the scope of our traditional telecom datacom area. But yeah, those are, you know, pretty hot topic applications, especially including for the integrated photonics, including for automotive vehicles, 3D imaging, robotics. And we added a couple examples, so you can see them. You can find them in the 11.4 release via the following links. I just show 2 of them here. And one more thing, we did the whole webinar dedicated to this topic around half a year ago. So please refer to this link and watch this on YouTube and find out more details. We also have a couple videos on our YouTube channel showing, for example, this particular example in more specific details. But just to give you a very brief overview of what's going on here. So we have here pretty much advanced design for the frequency modulated laser. So it consists of gain section simulated with Photonics TLM, and also the cavity is created with Bragg gratings. And actually, as you notice, here we use different Bragg gratings than based on Photonics TLM. Again, in this case, we found it more useful. So you see one of them also as a sampled Bragg grating. So they form the cavity, and we have phase shifter here to actually tune the frequency. And we also have a linearizer here, so that's a nonlinear function which predistorts our electrical signal, because inherent intrinsic the response of the laser is nonlinear, and we need to compensate for those effects. So this frequency modulated laser signal is split into probe and reference, and probe travels through the free space reflected from the object and received back, where it is mixed with the reference signal. And due to some frequency shift due to Doppler effect and some delay, obviously we have some delay while traveling back and forth. Due to that, we have some beatings in the electrical signal, in the detected electrical signal, which could be detected on the RF spectrum. And from this position of this frequency, we can easily define the position of the distance to the object and the velocity if the object is moving. But yeah, our main thing here is actually that we could combine those very different types of simulations. So as you can understand, here is the simulation. They are pretty close. They're very close. The components are really small. They're very close to each other. And here we have like meters, or maybe kilometers of distances, meters of distances travel into the object, and we effectively combine those simulation in one schematic, in one simulation. So for that, we have this little guy here doing the conversion of the sampled signals to the block signals. Let's just take a look at the results real quick. So yeah, we may have some transients because the simulation is pretty realistic. Yes, we may have some transients at the very beginning. Yeah, that's our electrical signal, driving electrical signal. That's our frequency, modulated frequency, output of the laser, transmitted signal, and the received signal. So as you can see, they're shifted in the time domain, and that's a detected electrical signal and its RF spectrum. And from the position of this frequency, we can define the distance. So that's one example. Maybe I don't need to finish it. And another example is actually showing the two-dimensional beam steering. And the principle here, again, I'm not going to dive very deep into the details. You can check it on the webinar. But a few things which I would like to highlight here that we actually doing two-dimensional beam steering due to two effects. So one is actually here at the end we have the gratings. So depending on the frequency we have our spot being transmitted on different angles, and also we have so-called antenna effect, where due to different phase shifts we can steer another direction, and the different phase shifts are achieved due to two things. One is that we are changing the frequency of our laser here, and another because of this array here. So that's actually an array of waveguide, and that's one thing which I would love to highlight here. So we have instead of putting manually 39 waveguides here, we use this MapGR module. They're so-called high order functions model, and they're used for creation of arrays or chain of modules. So this guy just repeats anything we put here as many times as we wish, but we can also vary some of the parameters. So that's very convenient. So we, instead of putting 39 waveguides with different length, we can just use this structure. And because of different length and because of the dispersion in the waveguides, we have different phase shifts for different frequencies. And that's how we achieve the steering in another direction. This simulation takes a couple minutes to finish, so I pre-run it already, and yeah, and we can see the points on the screen transmitted in two dimensions. And actually, we see that the field of view is pretty large, so around 15 degrees in one direction and around 3 degrees in another direction. So yeah, please explore those demos. They're part of our tools. We continuously working on more examples. So the examples we showed today are not the only new examples we created. So that's approximately the full list of the newly added and some of them like significantly updated application examples. So please take your chance, take your time, explore them. As usually, so the same list is given also in our release notes document, so please explore this one. Install 11.4 version if you didn't do this yet. Shoot your emails at support@vpiphotonics.com, so we are happy to respond to your questions there. And just to give you a heads up, we have two online events coming up in the next couple months. So on July 19th, we have a webinar dedicated to our simulation tool for modeling fiber amplifiers and fiber lasers. So if you are working on this kind of applications, please take a chance and explore this webinar, join this webinar with us. And then finally, we don't have the fixed date yet, but we are definitely planning to have an open training. It will be online open training. So if you interested in training, again, please subscribe, write on support, and we'll be providing the information about the open training as soon as we have it. Yeah, with that, I'm really thankful for you joining this session. Thank you again for your attention.